read-only mode.
Good morning, this is George Laird talking. Welcome to our seminar on using small connection elements. And I class these as the RBE2, RBE3, and CBUSH. I'm not going to get into the RBE1. I've never used it. And I'm just going to go, this is going to provide you guys with some theory that I've gleaned together. And I'll quote my references, where I'm getting it from, and the process. And this is actually the second seminar I've done on connections. I find them very intriguing, useful, difficult, so on and so forth. Along with me on this panel, I have my senior staff engineer, Adrian Jensen.
Hello, everybody. Good morning.
Yeah. He'll be available to answer questions. So if you guys want to chime in with questions, then he can answer them while I'm going through with the other stuff, so you guys can maintain workflow. Yeah, what I'm bringing up here, where is it? There it is, the PowerPoint. All live. What I want to show here is, we get these questions.
I think you still got to show your screen.
Oh, no. All this time. Thanks, Adrian. That's the thing with the webinars. People can't speak.
There we are.
Yay. Did someone ask the questions like, where's the damn screen?
No, I just figured.
Oh, good for you. So we get this question like, what the heck is going on? Because this webinar comes in as predictive engineering. So that is the analysis side. All we do is stress analysis under predictive engineering. Well, vibration, CAE, LS-DYNA, drop test, everything, computer simulations. But we are part of a larger company. We are part of Applied CAX. And Applied CAX has Sherpa Design, which is design, CAM, team center specialists, designers, and then we have the CAE side, predictive engineering. So we have two account managers. We have Kyle Dunscombe, who some of you guys know, and Ian McGagey. Then we have everybody else underneath, and we're a Siemens solution partner. Lots of different clients who would speak well of us, and a lot of you guys know the predictive side. 16 years consulting, training, sales. We do the training. NX training and services, CAD/CAM, Team Center Services, sort of rare, and Portland, Oregon. Of course, it never looks like that. Maybe 10 days a year, 15 days a year. Usually clouds, but you get the occasional picture. To the seminar, why you guys are here. Small connection elements and how amazingly useful they are for FEA modeling. And this white paper, what we'll do is that once I finish with the seminar, this is all being recorded. We'll upload the seminar, we'll upload the white paper, and also I have a bunch of FEMAP models to go along with it. And so you guys can do some work on yourself. And so this is the layout of it. And this, as I mentioned, is a follow-on paper. And I hope this isn't too jumpy. What I want to show, I'll be using FEMAP version 11.0.1. The dot release is out. You can download it from the Siemens GTAC website, or you can contact us for this download link to go direct, whatever you like. But this is what I'm recommending people jump on and install. It's a fixed-up version. For you on this seminar, I mentioned this is the second one. If you go to our website, Predictive Engineering, it's going to ask for a little username. And that's in our email signature block. Every email that we send out to our clients has this little username and then nothing for a password. And this is the seminar that I did about a year ago. And it was more nuts and bolts. It was more of like, okay, we have forces through an RBE2. How is it extrapolated? It's rigid. It was more of a technician seminar in a sense, and it left me feeling that, well, I needed to go a little bit deeper to really explain what was going on, and it was another attack. So I came back in, and I wanted to come at it from a little bit more of a theoretical standpoint, because it'll give you guys a better understanding. It'll make you feel safer in how to use these elements. That's where I got to start out. They're not exactly elements. It's something just the way it started out to use it. But they're multi-point constraints. Our rigid body elements are not quite elements. In the sense, elements classically, when I think of elements of FEA, F forces equals stiffness times displacements. F equals KU. The K is the stiffness terms. And if you've had some FEA classes, you go, yeah, you create the elements, you make stiffness terms, you dump them into the K matrix. You're solving, you know your forces, and you're solving for displacements. Well, multi-point constraints, they don't create stiffness terms. They never create anything that goes into the stiffness matrix. What they are a linear relationship between the displacements, the U terms. That's it. That's it. That's all it is. Linear relationship. You have a bunch of constants, A1, A2, and then the U's represent degrees of freedom. So if you have a plate node or a beam node, each node has 6 degrees of freedom, and to fully define it, you would have U1, U2, U3, U4, U5, U6 would be one example. People do different nomenclature, but each of the U's represent a degree of freedom and a constant. And so what you're doing on a multi-point constraint is that you're setting up a relationship between certain sets of nodes. And I go into this more on the white paper here. And I want to make this more of an overview, this discussion. If you guys need to really dig in and get more, you can come back to this white paper, or you can email us, or you can call us up. So this is when we first jump into introduction to constraints. I'm leveraging materials. You can see from here, the NX Nastran user guide. All these materials come with your FEMAP install. If I go into FEMAP, I got to figure out this tab a little better. Right there, there's your FEMAP 11.0.1, and I've done some customization on colors under Help, NX Nastran. And this is the 8.5.1. So they've released a bug fix with it. It's a little bit like, I don't want that. Where's the NX Nastran 8.5 documentation? And here's it. And you got the NX Nastran user guide, getting started. They're really quite useful stuff. And in here is where I pulled out that from the user guide. But I've used 3 references. I used the user guide, the element library reference, and I've also gone into the theory manual. And then I have another very older reference from MSc Nastran on connections. So, okay, back to here. So this right there, create constraint equation, that's a multi-point constraint. That's in FEMAP. Some of you may have seen it. I got to tell you, I haven't seen it. I've never used it. I feel like I'm lacking sometimes. So web seminars, you can see the various, I try to keep, there's our old one, here's a new one, our reference, R2, first RBE2. You gotta, and this is due because I was running it with the new V11 where you're attaching to results, so I'm not gonna attach that. I'm gonna go right there. And then it's model, constraint, nodal. Oh, that's not it. Where is that?
You might want to slow down a little bit, George.
Okay. Constraint.
Just for the screen lag.
Thank you. Where is that multi-point constraint? This is how often I use it. I can't even find it. There we go. Terrible, isn't it? I don't really over-practice these. I went through it with Adrian yesterday and make it up. But this is, if you're really clever, this is how you would make a multi-point constraint. If you're really clever, you could figure out the relationships to create your own rigid body element or your own RBE3 using this dialog. Okay. Back to here. Introduction to constraints, NX Nastran user guide. So let's get to the real concept, the real core nugget of this discussion. Multi-point constraints are elements that the way that they're defined, the way they work, are in grouping of independent and dependent degrees of freedom. That's the whole gist. Independent, dependent. Because what you do is you start out with this equation here, sum to 0. Then you divvy them up to independent and dependent DOFs. So we have F equals KU, which is our equation of motion. The MPC, there's matrix algebra for that setup. AI, which is your constants times your displacements, or your DOF. And then you break them up in as US or UM. US are your independent, and UM are your dependent. And this is Nastranese, and you're going to see these terms US, UM pop up in error messages. But the concept is you're going to break up your degrees of freedom into nodes that are masters, independent, and slaves, dependent. And that's terminology very common out there. And using these relationships, you can define, of course, all your dependent nodes can be defined with your independent. They're removed from the matrix algebra. Once this operation occurs, they're gone. Ciao. They're removed from the side at F equals KU. They're gone from that U column. And this is an important concept. Your dependent nodes are gone from the U column. You can't attach to them. You can't apply other constraints, like a single point constraint and SPC, because they're not there. They're defined as part of the independent node set. So that's the basic terminology. If you can walk away with this one concept, that's the big key. Okay. So where does this hit the ground? Where is this useful in your modeling world life? I think many of you guys, if you've used rigid links, you've run into this little issue here. And I'm going to go to FEMAP and bring it up and show you. So let's make this full screen. How's it going, Adrian? Is this tracking?
Yeah, it's looking good.
Good. Okay. This right here, let's see what sort of element I have going on. That's an RBE. The independent node is at the center right there. And if I want to, let's put on, it's not going to let me because it's in this box. And I'm constraining it just in the Y, degree of freedom, and 2 and 3, like that. Now, these are the dependent nodes of freedom, and they're only in the Y. So now, if I were to go in, constraint nodes, and if I were to grab that node, fix it, apply an SPC to that degree of freedom, like that. Now, in the white paper, this element also has the TZ degree of freedom enabled. But I'm doing this slightly different. Well, because this model has a little history, but I don't want to follow too verbatim. And then here you go. You got the fatal error and a little bit of anxiety, like, oh, geez, what's screwed up? And I'll go, this is something, I'll click on F06 and I'll expand the pane, and it's on my other monitor, and come back over here. Even though I turned it off and everything, it's still thinking it's alive. Come here, there you go. Let's go back up where it is. And there is our Nastranese right there. User fatal message, grid point 2, which is for node, component 2, which is our degree of freedom. Component 1, 2, 3, 4, 5, 6, of course, track 2 in global Cartesian, X, Y, Z, RX, RY, RZ. So this is saying that component 2, which is the Y direction, illegally defined in sets UM, US. Well, just from this part of the seminar, well, that makes perfect sense, because what we did is we applied an SPC to a dependent degree of freedom. It doesn't exist because it's been set up to be defined as a function of the independent. Now, if we just went in and changed that, let's go down here to the tree, edit constraint. If we apply it to like this is just sort of cute. It makes the point that we're going to do everything but that. Okay, double click, redraw. I'll run it again. And of course it's going to work just fine. It doesn't care because it's not a dependent. What do you think, Adrian? Is that have I belabored this point? I don't want to belabor things. I want to just you know, get it.
That sums it up. It's our, what did we call it yesterday, the double dipping.
Yeah, that's
like
it.
If it's on RBE2 and you're using the DOF2, then don't constrain it with DOF2 because it's going to have a problem.
Yeah.
Don't double dip.
Yeah, it's like, but at the same time, know what you know. And of course you can apply constraints to your independent node. Edit where applied. I gotta admit, I love the tree at times. I mean, it's just, so know what you know. So in this sense, of course you can apply it to your independent degrees of freedom. And if you wanted to, they're all 6, because it doesn't care. It's independent. Of course, now nothing's going to happen because you fixed it. Now, I wonder if anybody out there has raised their hands and say, well, look, you just got on this long tirade about not applying SPCs to dependent degrees of freedom because they're gone, yet you have a force. Yet you have a force applied to that dependent degree of freedom. Well, that goes in, and because F equals KU, multi-point constraints only affect on the U side. Your Fs, your forces, you're free to do anything you want. Dependent, independent, it doesn't care because it's on the force side. So there's some really interesting things that also, for a few of you guys that have had some matrix math, you're saying, well, this is interesting because it operates on the constraints. It will also tell you it's a linear element. That if you do a geometrically nonlinear analysis, it has no idea what the heck is going on with a rigid link. Anybody that uses LS-DYNA, they know rigid links don't exist. They call it a coupled nodal rigid body. You take a group of nodes, they couple it, they turn it into a rigid body so it can spin and move. If you use solution 601, again, rigid links don't exist. They get rid of them all. They put in little beam elements. It is something for linear analysis because it operates only on the constraint side, only on the displacement side. So these are really useful little points that come up. Once you sort of know how it all fits, it'll give you more confidence. Now, I've been talking about the RBE2. The RBE3, it's the same but different. Now what you're doing is you're switching it around, and it's still independent and dependent nodes. But now you have one dependent node and as many independent nodes as you want. And what you're doing is you're slaving that one dependent node to this whole bunch of independent nodes. And it doesn't, due to that mechanism, you don't get rigidity. No rigidity is applied. But what you do get is you get transfer of forces, movements, and it's nice and smooth. And it's very clean. But there's some drawbacks. There's some really sneaky stuff that goes on with RBE3s that can cause a little bit of problems. But I think once you get through with this little seminar, it'll be a little easier. So what I'm going to do is I want to morph that RBE2 from that one model. I'm going to morph it into an RBE3. And I want to show one of the big things that come up with that. So let's go back to here. And I'm going to undo, get back to the starting point. And I'm doing Control-Z. I try to do a little bit sure I don't do things that are totally unknown. And now go to Modify, Edit, Element. But of course, I could go like this. I like to use the selector as much as possible. Edit. And we're going to convert. Notice here we only have the TY. When you convert, it tries to follow that practice. But it's not quite, don't trust it. Here's our independent. And notice that in FEMAP, they always keep the dependent on the left-hand side. And here's the independence on the right-hand side. This is the new format that they changed to, I think, on V10 or something, V10.1. And there's good reason for it. it's more logical independent. And here's your weighting factor, which I'm not going to get into. It is one of those things that you can do some interesting things with, and I've never bothered figuring it out. I'll cross that bridge when I get to it, but it's the way it averages. It takes each node, has a weighting factor, and you can size it. And I'll let you guys dig that in. If you want to know, you can read the manual. Okay, enough said. So this box here, it's saying here that node 2, it's a little small. Hope you guys can see it. It's saying it's using the translation in the Y, but with no rotation, and a weighting factor of 1. Well, if we run that like that, that's just not. It's if you do it default, this is what you get. And this is one of the bridges you have to cross on an RBE3, is that it is treated as you're making a stiffness, you're making a relationship among the dependent and independent nodes that has to be stable, and that you're in an RBE2, you come out of the gate with the independent nodes being 6 degrees of freedom and completely stable matrix-wise. That's the concept in RBE2. It always comes out of the gate stable in the matrix. Where in RBE3, since you're defining degrees of freedom on the independent nodes, it doesn't come out stable. And that screws people up all the time. And it's one of the big dangerous parts. So here it says, right here, RBE3 element, 1,1 is singular. It has mechanisms. It's moving in space. Add more DOFs to the connected points to ensure that they can all constrain all 6 rigid body nodes of the element. And there again, they use elements. But it's not. It's not adding any stiffness terms to the matrix. So, okay, what do we do? On something like this, let's go back to here, edit, and I'll take the nodes and reset. We still just one dependent node. And now, this is very common. This is the default, the pinned nodes like that. And a rule of thumb on RBE3 is you don't want to over-constrain it. And over-constrain means when you are using RY, RZ, RY, RX, the rotation of degrees of freedom. Over-constraining means that it doesn't find a correct solution on your RBE3 when you over-constrain the element, when you don't have a minimum set. And I'll try to get into this a little bit more. But in this action here, if you were to think of this like a rigid body moving in space, you would say, okay, I've covered 3 degrees of freedom here at this point and this point. So it can't move this way. It can't move this way. It can't rotate around this axis. It can't rotate like that. It can't rotate the other two. And we'll just run it like this. Oh, and I forgot to show that. You can see that it shows up here that you got P, translation, X, Y, and Z. Nothing in rotation with a weighting factor of 1 on both nodes. So we'll run it. And it comes back with another warning message. Well, fatal error. Same thing, it's singular. User action. Add more DOFs to the catch point sure the constraint all 6. Well, fine. You'd think it'd tell, if it was like a standard linear analysis, it would tell you what degree of freedom was unstable. Well, some of you guys out there already know what the problem is. The problem is that this makes sense, but it's like a beam element. You got to prevent drilling. You can't drill down the length of the element. So you got to keep it from drilling. So we got to grab the Rx degree of freedom. There. Of course it runs. No problem. Fine. Results. Deform. Voila. And I wonder if I enabled the free body on this. Display free body. There we go. I did. There. Very pretty. I love the new free body. And no moments are transferred because all we're doing is we're saying transfer in the Y direction. And in my other connection seminar, I go at length about moment tracking and distance and spatial relationships. And it's useful, but I really wanted to concentrate on the theory about how to use it and why, and this rotational thing of RBE3. So, Adrian, what do you think?
Yeah, that sounds good. Sorry, I was over here doing some questions.
Okay, yeah. I know there's it's I honestly I don't want to have everybody go to sleep. It's you can do this with rigid elements. There's so much. I'm just trying to skim it, get through. Thing about R elements is that you can daisy chain them. This concept independent and dependent. Yeah, you could take an independent node of one RBE2 and you could chain it to a dependent. You could chain it to another dependent node. You can make these weird setups, and they work. I've seen examples of it. Rule of thumb: don't daisy chain. Don't connect dependents up to independents, or independents to other independents. You can do it, but it just gives me the weebie-jeebies to like tracking stuff and determining stuff. RB3 elements can be a bit brutal. Think of them as small little free bodies floating in space, and you have to tie them down, but you don't want to over-constrain them. My prior seminar has an example of an over-constrained RBE3. It takes a torsion tube. It shows that you have a RBE3 around a torsion tube, and you have all the rotational degrees of freedom enabled, and it blows up. So the concept is, in general, you're only using the translational degrees of freedom on your independent node. If you do that, you're going to be safe. If you can get it to run only using translation, good to go. And this is only use translation DOF for independent DOF. If rotation DOFs are absolutely necessary, test as if your life depended upon it, which means you check it, and you remove it, check it. So do not hook an RB3 into RB2. But RB3s, they're really useful. We're using them all the time. I want to go a little bit into applications here. And this is really the classic. People are using them for bolted connections. And maybe one day it'll all be contact and all solid models and so on and so forth, but it'll be a while because it just adds so much computational overhead, and also you got to debug everything. And as you add complexity to a model, it really you introduce problems. You can introduce other problems because you miss checking stuff. You spend too much time mucking around in details, and you can miss bigger stuff. So I really strive to really build the most elegantly simple model you can, which is harder to do because you got to validate your assumptions. So the brute force method can be more, maybe it can be more visually satisfying at first glance, but there can be problems hidden. There's the thing. Errors have occurred reconnecting to result files. Well, because I set it up. So this is my RBE3 to do the force to the load transfer. And you can see here it's translation, TX, TYZ, no rotation needed, and I'm only moving the X direction. That gives a nice uniform force application. Makes it quite nice. Just grabs that force, moves it down to there. Okay, let's take a look at our, well, I can use this. I try to do things a little different in every seminar. I want to select multiple. You see, I try to do sometimes non-standard workflows. Those are in the selector now, and you can see it shows there. I'll right-click. I'll just go edit. It brings it up. So those are 6 DOF, like that. They're all 6 DOF enabled. So let's go ahead and run that. It's done. Model info, results, right click, contour. 22,000. We've all seen this, and it seems quite reasonable. So what I'll do is, let's change it around. See how I click back to element? I'll go right click, edit. It's all 4 elements are in the selector at this moment. And now let's just make it translation. Yeah, and if we had a lot to do, we'd write an API and automate it. Grab all, change all. We'll rerun. It's done. There, 16. And what were difference? People would say, what are you really doing? What are you idealizing? Well, fully rigid would be the most massive bolt head, high grade, stainless steel digging in, being fully on it. And even that, I think, is unrealistic, because you wouldn't be locking in the deflection, the rotation. So I really think the 6 degree of freedom spider is you're overly constraining it, and that's why it pops up with the hot spot, because it's overly constrained. And the pin is more realistic. You're letting it, it's still locked in here, but you're not locking in the displacement. So I like that. Okay, so now let's convert to an RBE3. Convert, and here it did it correctly. It grabbed the 3, no rotation. Convert.
You might want to do that again a little slower. There's a little bit of lag there.
Okay, so I said on the conversion from a 3 degree of freedom, where the dependent degrees of freedom have only the translation, straight over to an RBE3. It works. It maps it. Takes these 3, maps it 3 over here. Pretty clean. Of course, because this is an example. I still remember this guy's comment many years ago. This presenter said, well, did you enjoy the demonstration? And the guy responded, well, of course, I'd have to be a fool not to enjoy a demonstration, because it's all canned and perfect and well put together. So this isn't quite a demonstration. So this is, I got to show the deform shape. There we go. Here's an RBE2. There's our deflection, and this is one being pinned. And here's an RBE3, and you're just going, that just doesn't work very well. I don't like that. I capped the legend at 20,000 just to make it. So I know there's some people out there, I'll leave unnamed, that would say, oh no, boat heads, you got to use an RBE3. Don't want to transfer too much stiffness. And I'm going, you sure about that? This example shows that they're useful, but you want to understand the physics of what you're doing. So not quite so good. Okay. Keep moving along. I got lots of material. I got to go quick. There's homework exercises, take models, play rigid bodies. For you guys that are not that familiar with using the FEMAP's free body diagram stuff, these little models are perfect to play around with, along with your rigid links, because they're small, they're quick, and you can sort of hand calc out what's going on. Okay. The illogical RBE3. This is where I show the comparison. So, and this one here is all pinned. This one here, I actually constrained the independent degree of freedom with 6 DOF. And it says here, 6 DOF independent. And the independent are around the perimeter. So what you're doing is you're trapping more of the motion of the plate. And it's a little better, but it's still screwed up. Okay. Here I talk about with RBE3, it's impossible to force a rotational stiffness into the structure as per the formulation. Only the load is transferred And so what I'm referring to is that on an RBE2, you lock it in. You get rotational stiffness. On RBE3, you can't because of the way it's set up here in this model. Lots of little details, and I don't want to get lost in the details. I want to keep the overview: independent nodes, dependent nodes, constraint setup, constraint relationships, and lining things up. So this is one of the things why we really like the RBE3. Why it's worth the pain to go through, figure it out. This is where we have a mass at the end of this multi-point constraint setup. This is an RBE2 on the left. And no matter what you do, oftentimes you always get splotchy stresses. It just grabs, it doesn't smooth because it's rigid. It's imparting rigidity to the structure. On the other side, on the right-hand side, we have an RBE3. All set up, 3DF for the independent, 3DF on the dependent. And you get this beautiful, smooth-looking load transfer into the body. And in this case, the RBE3, since you have multiple points you're attaching to, it's stable. You know, stable, fits, works perfectly. Okay. Thermal. This is actually a big issue for people doing a lot of thermal work, especially like, say, satellites or pressure vessels with thermal loads, motors, all sorts of stuff. And this opens a really interesting discussion about multi-point constraints. When you switch over to thermal, and let me show where that is. Okay, let's go back to element, right-click, edit. It's this thermal expansion down here. And it's on RBE2 and RBE3. And honestly, I don't know what you would do a thermal expansion for in RBE3 because there is no rigidity, but it's there. RBE2, of course, it's rigid. Thermal expansion is really a big deal because what can happen, let's go back to the PowerPoint, and you guys know this already. This little simple model here has a uniform temperature increase, delta. We're just saying it heats up from a reference state of 0 strain to 100 degrees F and expands. Well, a rigid element is rigid. So it's going to stay rigid. As things expand around it, it stays rigid. You get these high stresses. For many years, it was people would just sort of live with it, or they would take it out, put in beam elements, put in springs, all sorts of things to get around it. Well, what NX Nastran does is it switches. If you need to have coefficient of thermal expansion, it switches the element formulation from a rigid multi-point constraint to a regular element, and that it adds stiffness terms to the K matrix. It actually switches it to they call it a Lagrange element in the manual. And a regular rigid element is a linear element. It makes sense, sort of. And so when you switch it over to a CTE element, it's no longer a classic rigid. It's a Lagrange. It's like having little mini beam elements. Except the only thing that Nastran will do for you is it adjusts the stiffness terms that it adds to the matrix such that the matrix won't become ill-conditioned. It sort of adjusts it. And they call this adjustment method the Lagrange multiplier method. So a little interesting background is as soon as you switch over and use the CTE method, it's no longer a rigid element. There's also another little thing that you have to do. And it catches people all the time. So you think you change it and you'd be good to go, but you're not. Right there. Rigid element thermal expansion. Because it's changing. It's a big time hit to the analysis process in the sense it's changing the element formulation from a rigid to a Lagrange. There really isn't much of a performance effect. In fact, I was reading the manual. It says it can improve the performance of the model. So a little interesting, a little gossip. And in the white paper, I actually show it out. I said it's a two-step thing. You got to set the coefficient, then you got to set it. And once you do that, it looks beautiful. And of course, here's what it is. It's rigid, linear, and this is when it's switched over to our Lagrange rigid link. So there. Now you know about CTE. Summary application. What I'm breaking this PDF down into, and it's sectioned, and I like to have a summary after each little section, and then I of course I summarize again in the front. So summary application note on MBC is RBE2 transfer stiffness as a rigid body. You can control the DOFs. RBE2 is numerically stable, 6 degrees of freedom. RBE3 is not. You also get the spatial relationships of both elements, force interpolation capability. It's really worth the hassle. We use it for anytime we got to attach math onto a structure and we want it to be flexible. RBE3. Adrian, what else do you use it for?
Let's see here. The bolt heads are obviously the most common. Sometimes when you have like linkages or pins or some sort of mechanism, you can get creative with which degrees of freedom you add stiffness to, and you can let it pivot one way but provide stiffness in another way.
Yeah, lots. It's every model that I can think of. Anything that I'm really idealizing, I have R elements within it. And interpolating stresses around it can be tricky. That's why it's useful sort of understanding what it's doing. It helps you interpret the stresses that you're seeing, and whether they're truly an artifact of the R element over constraining the material, or whether they're real. I mean, how do you discount stresses around an R element if you don't really understand what it's doing? So hopefully this little theoretical background will provide that. And then MBCs operate at a constraint level, and they do not create stiffness terms within the K matrix per se. They create relationships with the constraints. Although this makes these connections only suitable for analysis work that is strongly linear, they also do not perturb the matrix with high stiffness terms as spring elements. Because somebody must say, oh, well, I just use spring elements. Well, I haven't seen this, but I've been told enough by other people in reading the manuals that if you use really high stiffness terms for springs, you can cause other things to go bad in other places. And to get equivalent stiffnesses, oftentimes you have to use crazy high spring values. So, okay. How am I doing on time here? Take a look.
It is 9:13 here on the West Coast.
Oh, I gotta hurry. I really, it's an hour. Working with CBUSH. CBUSH has always seemed to get left out at the end. Happened before. Jeez. Well, a lot of when I see models, and if I see CELAS, I usually comment to people that have submitted them that, have you thought about using the CBUSH? The reason why is I've had bad experiences with CELAS, and even the Nastran people say the only place you can really use CELAS is when you have coincident nodes. And you have coincident nodes and you want to attach a spring between them. Myself, I don't like having coincident nodes in models because even though the FEMAP merge method, it has safeguards against merging coincident nodes with elements attached to them. That's a built-in, that's safe merge that came out a couple years ago. I don't know, I just don't like it. I like having a little bit of gap between my nodes. So if you have a gap, this is going to cause problems. The CELAS is just not set up for it, and that's what the Nastran manual is telling you, that you can have bad things happen. The way around that, CBUSH, that's the new default element. When you hit spring damper, it's going to default CBUSH. I think of this as a 6 degree of freedom beam element. You can tailor the stiffness in any 6 degree DOF, and also for dynamic simulations, you can tailor the damping This field here is structural damping. It got truncated in their dialog box, but it's another form of damping. It's not structural stiffness. On CBUSH, you can have these values here correspond to the element orientation, just like a beam element. Down the length of the element is X, and then you have Y and Z, and the Y and Z is defined as you do a beam element. Voila. Or I'm always using the orientation coordinate system here, click, and global Cartesian. I get these patterns, and I always use the same pattern if I can get by with it. It's just one less thing to check. CBUSH, orientation coordinate system, then I know I look at global, go X, Y, Z, done. That's my thing. And I go and I talk about why they're useful. They're really useful for nonlinear solutions. Solution 601 really likes the CBUSH, CLS, I don't know. Here I talk about my preference for orientation coordinate system, or this is the default summary of CBUSH. Since we're getting up to an hour, I want to get straight to my little example of why the CBUSH sometimes drives people a little bit crazy trying to figure it out. Okay, here's my, well, CBUSH, 6 DOF element. Well, look, we got a solid element. Has 3 DOF on it. Okay, in this little example, of course, tailored, we're going to pull up, and what have we done with that? Go to properties. We just have it one stiffness, and we're defining an orientation coordinate system. So Y up, 2. All good to go. Hit run. And it's all aligned. We can contour some pretty stresses. Look at that. Oh, okay, no contour. No deform. I could have just undoed faster. So now let's make this modify, edit. Well, I want to move by. I'm going to offset this just a bit. Ta-da, ta-da, ta-da. O1. So it's just, just a teeny. I should have offset a whole bunch. I don't know why I did O1, but just to show that if it's not perfectly collinear, failure, gone, F06, double click, expand the plane, degree of freedom, R3, R3. Well, R3 is a Z. I moved it in X. So you guys are mechanically minded. You're going, well, of course, you moved it in X. You're going to create a moment around the Z axis. And we don't have any stiffness around the Z axis. Well, we could do 1e to the 5 like that. Oh, I don't know. I did that too fast. I said, okay, let's add some stiffness. Let's add some stiffness to the R3. Remember, we're in the orientation coordinate system basic. And this is, I touched it and it moved. Okay. And it's the same thing, because that being like a 6 DOF beam, R3, it doesn't have anything attached to it because it's a solid element. It still creates a moment, but it can't react that moment down there. I want to show this. This is one of my tricks that I'll do, is that I just sort of go, well, fine. I really need that set up right there. This is a solid element. I'll just say no rotation. I mean, I could just do it like this too. Sorry about that. You guys can't quite see that. You see that little 6 right there? I mean, the solid element doesn't care. There's no stiffness terms in there, and it runs. And because now it's tied in there. Now, if we get rid of the stiffness in that side, This is the part I know I'm going a little bit fast. I want to slow down a little bit because I think I've lost some people. What I did is I told that CBUSH there's no stiffness. Right there. Even though it's fixed in that, I got to do a Control G. That background, 6, like there. I could use element shrink. Where is that? Oh, there we go. Ha, there we go. I'll just shrink that element. 6 degree of freedom. If there's no stiffness in that direction, even though it's locked, it's going to fail because it doesn't have anything to resist that out of that moment effect. And this is why working with CELAS can be a little bit tricky, is that you got to think of them like beam elements. I put 1e to the 5. So once I give some stiffness in that direction. And some of you might say, well, this seems like a lot of overhead, just use a little spring. And I guess I wouldn't argue with you at times. It does seem, it seems a little bit, look, I just want to put a spring on it. Why is it being so picky? Well, it's very useful, very functional. And with those highly useful, people say, I need a really powerful FEA interface that's easy to use. Not very many commands. Doesn't have a very complicated menu structure, but it needs to be really powerful. Yeah, good luck. This is the way the general form. Move by node. Point 1, point 1, point 1. Crazy ass in space. This is more common. Crazy ass in space. What do? Well, it's not that bad. What I'm going to do is edit constraint. You just fix all 3, right? And then you go ahead, you can go into CBUSH. Like that. So now what we're doing is we're giving it stiffness in all 3. Just run it. Done. That's my general format. My general format, if I had to attach CBUSHs onto solid elements, I just fix the 4, 5, and 6 rotation and off to the races. And I'm done. Okay. There's one last thing I want to show on this, is that this is with spacing. Okay, I'm going to undo. Well, what if it's coincident? If I make these things move to node, okay, right click, snap to point is enabled. Pick that point right there, it returns that nodal coordinate system. I'm going to move all 3 like that. Now look what happens. If they're coincident, I think some people are going to know, if it's coincident, you can't develop any moments. No moments are going to be developed because they're coincident. You don't need any stiffness in it. And it runs. No moments, no harm, no foul, coincident, voila. Just like a CELAS. Jeez. Adrian, what's your comment?
Sorry, I'm hammering away on questions.
Notes? Sorry, I know. Oh boy, summary of CBUSH. I'm sure. I don't want to see. So, and in the white paper, I do some basic comparisons. I flesh it out. I say, okay, it's like a beam element. And yes, it can behave like an RBE2 if you crank up the stiffness enough. I was sort of surprised. When I do these things, I have a very selfish reason for doing it because I learn a lot. It's it's really a good learning tool for me. I mean, I know this stuff fairly well, but boy, there's nothing like trying to have to really dig in and explain it piece by piece. And as a process, I pick up these little things like really to get a CBUSH to mimic an RBE2, I'm losing stiffness terms of 1e to the 7, which I find pretty extreme. I mean, 10 million. This is units English, psi per inch squared, psi an inch. So they're high stiffness to get it to match up. See all the nice little rigid body diagrams. And this is more normal when you loosen it up. You get this sag effect. And then this is where the difficulties with CBUSH, that's what I covered there. That was the most fun. I got to nail this down and get this all worked out. And the error messages that you can get, we covered some of that. And my little trick of just restraining 4, 5, and 6. This is my hat trick. Is that I went through all these problems, but don't forget that you can make it stable. I just tied in the 4 corners, and it's a CBUSH. There's no constraints applied. The load is at weird angles. You see I got a moment applied too to that center node. Everything works because with the 4 elements to 4 corners, you have a stable structure. All 6 DOF can be rendered stable by the translational degrees of freedom at each corner. Which you guys, it makes sense. You can work it out. So, special applications of the CBUSH for torsion, load. And this is some stuff we covered on our prior connection thing too, but I have always struggled trying to get good, clean load applications into torsion cylinders. And this is an example, it'll be on the web, is where you split it, and I'm joining the split with a CBUSH element. I'm applying the loads on both ends with the RBE2. Because you use an RBE3, because of the weighting function, you would actually have to change the weighting functions as a value of R in distance out here to the independent node. It can be done, but I sure ain't going to do it. So you can do an RBE2 in a cylindrical coordinate system, and it works just perfect. And Adrian showed me that. I was struggling with fooling around with that on that. He said, oh, look at this. So that's in the white paper. Some of you might have asked, what about this thing? Because I wanted to explain, nope, not there. Our old TAD. There we go. Nope. I wanted to explain in detail, what's this card? DOF. So when you look at this, you're a master of the rigid element card. You can see everything there, and you know what I mean. This DOF, it's a special trick. I've never had to use it in 16 plus years, but it allows on an RBE3 that you can apply a constraint to the dependent degrees of freedom, which just sounds completely wrong. You can't double dip. But what it does is it moves the dependent degrees of freedom onto independent nodes. It's a morph. It's a bastard child. It's there. I documented it. I think it's the first time I actually understood it. The second time going around. Isn't it there? Oh, boy. It'd be interesting to talk to somebody that said that, oh, yeah, using the just saved their ass on a project. Or like, oh, yeah, it's a standard for us. We use for this. It's developed for us. But here, it's in the notes. I show how to use it. And this is the key graphic, is that you can apply, here's your dependent node for your RBE3 at the center, and I fixed it. That's just wrong. And these are the nodes, and it's a cylindrical coordinate system. And I would never have figured this out on my own. So, but that's the gig. So those are our notes. And I made Look at that, 9:30. What a gig. And these are going to be published. Seminar will be published. Models will be uploaded. V11.0.1 is out. And that's what I would recommend going up to. I went through the seminar here. Oh, yeah. For you guys, there's going to be a FEMAP seminar, symposium coming up. And we're going to be there, too. It's going to be in Cincinnati. I got this flyer. Where is it? Oh, yeah, the keynote presentation is going to be Darlene Lee. That's going to be the Mars Curiosity rover. Everything on the rover was done with FEMAP and NX Nastran, all the structural analysis. There was just a little bit of thermal analysis done with this other product, this NX CAE product, but all the hardcore idealization, modeling structures, it's all FEMAP. And we have a link on our website to get set up. Also, we have our own flyer. We're going to be there out there in force. Adrian will be there. I'll be there. Kyle will be there. I may have a couple more engineers coming. I don't know how many people I want to have there. We're going to have some. We're going to have, what do they call it? Swag. We'll have some swag. Water bottles. Who knows? But the presentation, Darlene Lee, she should be outstanding. That should really be really a wonderful presentation. You're going to get to meet all the developers. There's going to be a round table for the developers. The night before, we'll have a chance to have drinks and dining. We're going to go for a couple of days. There's some other things to do around there. Then, last thing is, I wonder where that is. Oh, yeah. We have a training opportunity in April 16th. We still have a few seats left on it. We have this beautiful, handsome picture here. There's Adrian. It's a little low. He's actually not quite so fuzzy looking in real life. I know. You zoom in. And that's April 16th or something. I should be better with my dates. Okay.
I think it's the 15th to the 19th, maybe.
Oh, good. You're not even better than me. 16th, 17th. Maybe it is. You're right. Somehow I had it burned in my mind it was 16th. Okay. So that will be done with FEMAP version 11.0.1. Okay, that's it. Any other late-breaking questions I should grab onto?
I think we got most of them covered here. One of the big ones I was thinking of is this is all about idealization, and so a lot of people are asking, wouldn't it be better or more accurate to do it this way? And the short answer is you use these idealizations because you have to. You can't afford to model. You can't afford to model everything in great detail. So that's kind of
the truth.
Like one of the foundation of why would you use CBUSH or RBEs is sometimes you gotta be lean on the models.
I know. Why don't you model every bolt? Oh my God. Yeah, it's good enough. And then plus, what I really like about using the beam and bolt, if you've done bolt modeling, you just grab your little beam element, you put it in the data table, you pull out the axial stresses, and you pull out the shear. And we even have an API that will take the bolt axial and shear stresses, convert them in, forces, and convert them into stresses. And then if you've done any transmission analysis or other big stuff, you know that they take those axial and shear forces for your bolts, turn into stresses, and then they go all this. You got the preload factors, you got these other bolt degradation factor all in a spreadsheet, and it kicks out your safety margin, like bad bolt, good bolt. Remember that? The days of Cummings?
Oh, yeah.
Yeah. So it's a lot quicker. Hey, there's the train. There's the 935 Cascade. That's it. You guys know where to find us. And this will be up probably, give me next week till Monday, because it's always it's a lot of stuff getting packed up, shipped up. Anything else? Shut her down?
That's all.
That's all. Have a great day. turning this thing off.